And it's time to go through chapter 3. Chapter 3 is all about probability topics. So in this chapter, we're going to be talking about probability. So we're going to learn some key terms about probability first. And the key terms are really just that you know what I'm talking about when I'm saying different things, and you're able to communicate with me when you have questions. And then we'll learn how to calculate probabilities. For some of you, this chapter will seem like a bit of a refresher. And for some of you, this chapter will have all new information. We're going to learn how to construct and interpret different tables and diagrams that might help us organize some data that would help us find probabilities. And this chapter really allows us to gain a deeper understanding of probability. We will use this chapter as our foundation for probability knowledge as we move forward with this course. We need probability when we get into inferential statistics. So basically, once you have your descriptive statistics, then you take probability and you put them together, and you're able to predict things about your population based on your sample and your descriptive statistics. So we have to learn a little bit about probability before we can get back to statistics. So let's jump right in with some key terms. The first key term that we have is experiment. And an experiment is a planned activity that's carried out underneath controlled conditions. So we're saying, I'm going to flip a coin twice, and I'm going to record if it's a head or a tail each time. So we're carrying it out. We have controlled conditions going on. Maybe we're saying that it's the heads up each time. So we're very clearly defining some sort of activity that we are doing. The outcome would be a particular result of an experiment. So if we're flipping a coin twice, we could have heads, 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 tails, tails, heads, or tails, tails. One outcome would be just one of those results. So it'd be like a heads, heads would be an outcome of our experiment. Now, the sample space is the set of all possible outcomes. So the heads, tails, flipping the coin twice experiment had 4 things in the sample space: the heads, 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 tails, tails, heads, and tails, tails. Now, an event is going to be a subset of the set of all outcomes of an experiment. So it's a subset of your sample space, and it can contain any number of outcomes from 0 to all of the outcomes from the sample space. So like an event would be the event of getting heads before getting tails. Now, probability is a number between 0 and 1 inclusive. And this gives the likelihood that a specific event will occur. Now, events can be equally likely, and if events are equally likely, or outcomes are equally likely, or an equally likely experiment, that means that each outcome of the experiment has the same probability. So like thinking about our flipping the coin example, each time that you flip the coin, the probability of getting heads is 0.5, and probability of tails is 0.5. So your outcome, each one has the same probability. And as we talk about probabilities, we are going to use decimals or fractions all of the time because we're talking about a number that's between 0 and 1. I know that a lot of times we think of these as percentages, but we are going to talk about them as decimals instead. So a few rules that we have about probabilities. I know, I'm giving you rules, but these are important rules that we need to remember all semester long. Whenever we talk about probability, these 4 rules will apply. So first, probability is always between 0 and 1. It cannot be negative, and it cannot be bigger than 1. Second, P of A equals 0 means the probability that event A occurs is 0. And this means that the event A cannot occur. Now we also have that P of A equals 1 means that the event must occur. So the probability that event A happens is equal to 1, means the event must occur. And our 4th rule, and this rule we will see and use later on this semester as well, is the sum of all of the probabilities in a sample space is equal to 1. So basically, if we have an event where it's everything that's in the sample space, well, if we have everything that's in the sample space when we do our experiment, one of those things must occur, and so that means that it's a probability of 1. So the sum of all the probabilities in the sample space would be 1. So finding the probability of event A, we would need to count the number of ways that event A can occur, and then we'll divide by the number of outcomes in the sample space. If we wanted to find the probability of event A or event B happening, we would take probability of event A plus probability of event B and then subtract off the probability of them happening at the same time. If we wanted to find the probability that event A and B happen at the same time, we're going to find the probability that event A happens given event B did happen and multiply that by the probability of event B happening. We can rearrange this formula and look at it as the probability of A given B. And you've seen me read it a couple of times now, but that vertical bar that we have there between the A and the B, that is read as given. So if we are given something, we're saying we're assuming that this did happen. Now what's the probability of the thing in front of it? And then one last formula for us here on this slide, the probability of not A or the complement event of A or the complement of A, the probability of the complement of A happening is equal to 1 minus the probability of event A happening. So not A, when we have this bar over the A, we're saying everything that's in the sample space that's not in event A. So we're dividing our sample space into two things, event A and not event A. Now, a couple of these formulas can be simplified just a little bit if we have events that are mutually exclusive or if we have events that are independent. So two events are independent events if the following are true. So basically we're saying that the probability that one event happens does not influence the probability of the other event happening. And so these three formulas would hold true if two events were independent. Now, if two events are mutually exclusive, then the probability that they occur at the same time is equal to 0. So we have quite a few nice basic formulas to work with talking about probability. And before we get started in our examples, a lot of the examples that I tend to use, because there's lots of different ways that we can look at it and organize it and talk about probability with it, is a standard deck of 52 cards. And I realize that not everybody grew up playing with cards. And so we're going to just quickly define what a standard deck of cards looks like. So we're going to talk about a standard deck of 52 cards, and our standard deck of 52 cards contains 4 suits. The suits are diamonds, hearts, spades, and clubs. There are 2 different colors. The diamonds and the hearts are red, and the spades and the clubs are black. There are 13 cards per suit: ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, and king. The 3 cards that are considered face cards are the jack, the queen, and the king. And there is one of each of these in each suit, which means that there are 12 total face cards, and that would mean that there are 40 total non-face cards. All right, so this kind of gives us a little bit of a layout of what our cards look like, and we'll need this for a couple of our examples, especially the ones on our next slide. So when drawing a card from a well-shuffled standard deck of 52 cards, what is the probability that the card is a face card or a diamond? That means we're going to be using the OR formula. So the probability of face card or diamond is the probability of face card plus the probability of being a diamond minus the probability of face card and diamond. Now you might be thinking, why are we subtracting off the probability of it happening at the same time? Well, we're subtracting off this probability of it happening at the same time because we've counted it twice. We've counted it as a face card. We've counted it as a diamond. But we only want to count it once. That's why we're subtracting off. So the probability of face card or diamond, there are 12 face cards, so 12 over 52. There are 13 diamonds, so 13 over 52, and there are 3 face cards that are diamonds. So we have 12 over 52 plus 13 over 52 minus 3 over 52 equals 22 over 52, which we could simplify to 11 over 26 or write it as a decimal. As we write things as decimals, by a standard, we will typically round to 3 decimal places. Now suppose that 35% of people own cats. If you pick 3 people at random, what is the probability that they all own a cat? Well, here you're thinking the probability that all 3 own a cat is the probability person 1 owns a cat, and the probability person 2 owns a cat, and the probability person 3 owns a cat. When we're thinking and, we're thinking multiply. So we're multiplying each of these together, and what we see here is these are independent events. As long as we're randomly selecting people, these people most likely don't know each other or live together. And one person owning a cat doesn't affect somebody else owning a cat. Um, and so we would just take the probability that each person owns a cat, multiply it all together. What's the probability that person one owns a cat? 0.35. We're always going to change our percents into decimals. So probability that all three of them owns a cat, it would be 0.35 times 0.35 times 0.35, or you could look at it as 0.35 to the third power. Now, sometimes we will need to organize our data a little bit in order to kind of see what's going on with it. And one of the first ways that we will talk about this is by using tree diagrams. So tree diagrams can be helpful in organizing information to find probabilities that involve dependent events. So each time that we have a tree that branches off, what we're going to see is the branches must account for all possibilities, which means the total of the probabilities as we're branching off is going to have to equal 1. So what we're going to be doing here is we're going to be drawing a tree where we branch off multiple times. And each time that we branch off, we have to account for all of the possibilities. So like say we have some event and maybe there's 3 different things that could occur. So we'd have 3 different branches and maybe it's option A, B, or C. Maybe we're at a factory and an item came off of either assembly line A, B, or C. And maybe A is the most efficient and does half the work. Maybe B does 0.3 and C does 0.2. Notice that those add up to 1. Then we could have another time that it branches off and we could have that it works or doesn't work each time that we branch off. And I'm running out of space to write here, so I'm not going to do this smiley face, sad face down there. A little pin thing runs into the way. But we would go ahead and we could say, maybe most of the time it works if it's built from here. Maybe this branch isn't as effective. Maybe this one's pretty good. So we could have it branch off. And I guess you can't read my handwriting too well there. But what we notice is each branch itself, each time we're branching off, adds up to 1. But each time that we get to another spot where we branch off, we're restarting that adding up to 1 thing. All right, so let's look at an example. At a plant, it is known that the probability a new worker will meet their quota given they attended the training program is 0.72. Ooh, I can read. Okay, so the probability they meet their quota given they attended training is 0.72. The probability that an untrained worker meets their quota is 0.43. The probability a new worker attends training is 0.68. Draw a probability tree. So all we're having to do here is draw a tree. So we have a new worker, they either go to training or they don't go to training. So I'm using T with a line over it, meaning the complement event of going to training. Either go to training or you don't. And then each time you can either meet your quota or not meet your quota. So this is kind of the basis for our tree. Now, what's the probability that a new worker goes to training? Well, probability a new worker goes to training is 0.68. So the probability that a new worker did not go to training is 0.32. Now, what's the probability that a trained worker meets their quota? Well, probability that they meet their quota given they attended training is 0.72. So that means the probability that a trained worker does not meet their quota is 0.28. Where we were also given the probability that an untrained worker meets their quota. Probability an untrained worker meets their quota is 0.43, which means the probability an untrained worker does not meet their quota is 0.57. So we have a probability tree to run. Now what we're going to do is we're going to take this tree and we are going to use it, and we are going to find the probability that a randomly selected worker meets their quota. Now, that means we're wanting to know, how do we get there? How do we get to meeting our quota? We're thinking, okay, worker could follow this path to get there, follow this path to get there, right? So you could be a trained worker that met their quota, or you could be an untrained worker that met their quota. So really what we're thinking is that we are a trained worker and met our quota, or an untrained worker that met our quota. And then thinking about actually doing the math, we're saying the probability of being trained times the probability of meeting your quota given you were trained, plus the probability of being untrained times the probability of meeting your quota given you were untrained. Now, looking at the picture, we're saying we have these two different paths, and I'm going to make one of them a different color and have one red and one blue. So as we're going along the red path, and that is the probability that we were trained and met our quota, what we're saying is take these two numbers and multiply them together. Then as we're going along the blue path, we're taking these two numbers and multiplying them together. So we get that the probability that a randomly selected worker meets their quota is equal to 0.627. Now, I could go a step further and say, what's the probability the randomly selected worker was trained given we know they met their quota? Thinking, okay, trained given they met their quota. That means P of T vertical bar Q. Well, we've kind of figured most of this out before, right? We've done probability of trained and quota. That's up here in red, right? That's this part here. And then we've also figured out probability meeting your quota. That was our first part. So it doesn't take too much extra work to go ahead and say what the probability that they were trained given they met their quota is. Now, another thing that we can use to organize information is contingency tables. So a contingency table is a table that organizes information that's contingent on one another. It helps us see when we have mutually exclusive or not mutually exclusive events. So we are going to look at this contingency table here, where we have juniors and seniors were in a class together, and they all received either A's, B's, or C's. And we can see here that 8 juniors got an A, 13 juniors got a B, 7 juniors got a C. There's a total of 28 juniors. 12 seniors got an A, 2 seniors got a B, and 5 seniors got a C. There's a total of 19 seniors. A total of 20 people got an A, a total of 15 people got a B, and a total of 12 people got a C. And in our little class here that we were studying, there was 47 people. So what is the probability of getting an A? The probability of getting an A. Well, how many A's out of how many total? So we have 20 divided by 47, or write it as a decimal. What's the probability of getting an A and being a senior? There were 12 seniors that got A's. There were only 12 in that overlap of and. So it'd be 12 over 47. Or again, you can write it as a decimal. Alrighty. What about the probability of getting a B or a junior? Okay, we're thinking probability of getting a B or being a junior. So we have 15 plus 28. We've got to subtract off this 13 because it was counted twice. So one way that I like to think about it is if I circled these, I'm going to use my totals, and then I'm going to subtract off where they overlapped. And then I divide by the grand total down there. So 15 plus 28 minus 13 gives me 30 divided by 47. And again, you could also write it as a decimal. Alrighty. What about the probability of getting a C given you know that it's a senior that you're selecting? Well, if we are given that it's a senior, that means we know it's not a junior. So we can ignore anything that's not a senior. We're going to ignore the juniors. We're going to ignore the totals. Now, what's the probability of getting a C? 5/19. Tables make things a little bit easier. All right, final one. What's the probability of not selecting a junior that got an A? So basically, we're saying everything except for the juniors that got an A. So we could look at it as add all of those up and divide by 47, or we could look at 1 minus 8/47. Either way you look at it, well, you can do it. So you could have 39/47, or you could write it as the decimal form as well. Now, so far, everything that we've dealt with, it's been really easy to count, or relatively easy to count the number of ways that an event can happen. It's not always easy to count, though. So we're going to spend a little bit of time just talking about counting. So sometimes it's useful to have a tool to count things quickly. And so we're going to go through a couple of tools here. So permutations will be a tool that we can use to count when order matters. So it picks and orders k out of n things. And the formula for permutations is down here. There's also a calculator formula that I'll show you in just a moment. Then combinations, this is when order does not matter, and it picks k out of n things. It does not order them, it just picks them. And here's a nice looking formula. And then we also have the fundamental counting rule. It says to count the number of ways that a combination of events can occur. Events 1 through k have n1, n2, all the way up to nk ways that they can occur. And the number of ways that they all occur at the same time is n1 times n2 times n3 times all the way up to nk. Now, the permutations and combinations can be found on your calculator. If you're using a TI-83 or TI-84, there's a math button. You can go over to the prob or PRB menu, depending on the calculator you have. And then it'll have NCR and NPR. And the calculator just has R, whereas on the slides I have K. So let's go ahead and practice our counting skills then. So you're painting a house. You have 3 choices for the siding color, 4 choices for the trim color, 5 choices for the door color, and then how many different color schemes are possible? Well, this is using the fundamental counting rules. We're going to take 3 times 4 times 5, and there's 60 possible color schemes. Why is this useful to know? Well, maybe you're living in a city where there's a homeowners association and they're saying that you have 3 choices for your siding color, 4 choices for trim, and 5 choices for your door. And somebody's saying that's not enough options. Then you can say, well, actually, there's 60 possible color schemes. You're not going to look just like your neighbor. You can just choose a different color. So that's just one thing to keep in mind. That's a quick way of counting. Okay, what if you have a standard deck of cards? And when drawing 5 cards, how many ways can you draw exactly 3 face cards? Now, exactly 3 face cards means that in our 5 cards, we have 3 face cards and 2 non-face cards. You heard me use the word and in between. Notice anytime that I've used the word and so far, we're multiplying. So we're going to figure out how many ways to get 3 face cards, how many different combinations of face cards we could have when we're getting 3 of them. And then we're going to figure out how many different combinations there are for getting just 2 non-face cards. So when we're looking at the number of ways of getting 3 face cards, there's 12 face cards to choose from. Look back at that slide where we talked about our standard deck of cards. There's 12 face cards in the deck. We're choosing 3 of them. So that means there's 220 different combinations of 3 face cards that we could draw to the deck. And then we also need to get 2 non-face cards. There's 40 non-face cards. We just need a combination. The order doesn't matter. It doesn't matter which order they get into our hand. We just need them. So there's 40 of them. We need 2. So we have 40 combination 2. So there's 780 ways to get 2 non-face cards. So if we want these at the same time, we're saying and in between them. That means we're going to multiply these 2 together. So that means there is 171,600 ways to get exactly 3 face cards when drawing 5 cards. And we'll see how to use these counting rules with probability on the next slide. Let's do one more example real quick first. So you're selecting 4 people to be president, vice president, secretary, and treasurer for a club. How many ways can these 4 positions be filled if there are 20 people in the club? Maybe we're saying that the first person selected is president, the second one vice president, the third one secretary, fourth one treasurer. There's an order to it, right? It's not just, oh, these 4 people are the executive board. No, one of them is president, vice president, and if we swapped which one was president and vice president, that's a different one. So order matters here. So this is where we'd be using a permutation. So we'd have 20 permute 4. So we end up with 116,280 different ways to select these 4 offices. All right, so let's use counting and probability together. So card hand consisting of 8 cards is dealt from a standard deck of 52 cards. Find the probability that the hand contains exactly 3 face cards. Now we've done part of this already, right? We've found, well, something similar at least. We dealt with 5 cards. So we're going to kind of be able to use things that we've done before. But we need the number of ways to have 3 face cards in an 8 card hand. We did a 5 card hand earlier. And then we need just the total number of ways to draw an 8 card hand. So kind of using what we had before, we have 12 face cards. We need to choose 3 of them. So we have 12 combination 3. And then we need to fill the rest of the hand up with non-face cards. So 40, and we're choosing 5 of them. And then just to get the 8 card hand, we would have 52 cards and we're choosing 8 of them. So we have all of our combinations here. 12 choose 3, getting our 3 face cards into our hand. 40 choose 5, getting our 5 non-face cards into our hand, giving us a total of 8 cards. And then our denominator is just the number of ways to draw an 8 card hand. So there's 52 cards to choose from. We're just choosing at random 8 of them. Now you'll want to type this into your calculator like this because it's not very fun to try to type in the numbers, but go ahead and verify that you can get approximately 0.192. And you'll see a problem similar to this on your homework. One more here. So what is the probability that if 9 letters are typed, no letters are repeated? We're looking at the number of ways to type 9 letters with no repetitions divided by the number of ways to type 9 letters, allowing repetition. So in our numerator, where we're thinking, okay, I have 26 letters in my alphabet. Because I don't want repetition, I'm just taking these 26 letters and I'm ordering them. I'm picking and I'm ordering them because, typing A then B versus B then A, that's a different way of typing. So the order matters here. So we would have 26 permute 9 for the number of ways to type 9 letters with no repetition. Now, the number of ways to type 9 letters. Every single time that I type a letter, I have 26 options. First time I type, 26 options. And second time I type, 26 options. And third time I type, 26 options. And fourth time I type, 26 options. If I emphasized and enough, we're using our fundamental counting rule here. So you have 26 permute 9 divided by 26 to the 9th power. Again, type it all into the calculator all at once, or make sure that you have that answer function so that you can pull the previous answer to work with. And make sure that you can get to your calculator telling you that the answer there is 0.209. So that kind of sums up our chapter 3. Make sure that you email your professor if you have questions.